Okay, hello everyone. My name is Syed. My partner is Osama, and our AER 1516 term project is improving APF with potential speed functions for dual-arm robots. So this study focuses on dual-arm robots, which kind of mimic human hands. It's used a lot in manufacturing and assembly lines, food production, electronics, and more. As an example, you can see ABB's Yumi robot assembling some sort of contraption. For these robots, there are some challenges regarding multi-joint motion control and collision avoidance path planning between the two arms. Basically, you want to make sure that the arms don't hit each other. For one arm can be a sort of dynamic obstacle to the other. A popular collision avoidance path planning algorithm is artificial potential field, favored for its simplicity and real-time performance, but it has some drawbacks. Next slide. So what is APF? Artificial potential field is pretty simple. It's derived from potential field from the physics field. For robotic path planning, the idea is to determine how a robot can navigate through a space with known or unknown obstacles while minimizing collisions. In APF, a robot is attracted to a goal point through an attractive force, like two opposite charges, and repulsed by obstacles through repulsive forces, like similar charges. These charges are artificial, but in theory, they apply a net force to the robot to guide it from a start to a goal, as you can see from the image. A major issue is local minima, where the robot could be stuck between equal but opposite attractive and repulsive forces, leaving the robot stationary and unable to reach the goal. Example of that is in the cave that you can see. Other issues include oscillatory or jittery movement due to constant fluctuations in forces as the robot travels, and the goal unreachability due to a large obstacle nearby. There have been developments in this field to tackle these problems, and we'll cover them briefly so you have an idea on how these problems can be tackled. All of these are cited as inspiration for a proposed method. One is the gravity chain-based APF that simulates the rubber band that's connected from a start to a goal. Instead of the robot, this rubber band is under the effect of gravitational potential forces changing shape to avoid the obstacles, as you can see in the first picture. The robot simply follows the path tangent to its curvature. This solves the local minima problem in oscillatory motion, but it's being relegated to static obstacle environments and isn't really the best fit for us. There's also APF and RRT, where traditional APF guides the robot, and in the case of local minima, RRT, a sampling-based planning algorithm, pulls the robot out or causes random disturbances. This was tested on a cable-driven parallel robot, which has a specific workspace called the wrench feasible workspace, WFW. It's kind of seen in the second picture there. Well, it solves the local minima and oscillatory motion problems. Dealing with two path planning algorithms is a little too computationally expensive for us. Lastly, there's new point APF that, in the case of local minima, places a dynamic attractor point away from the obstacle to pull the robot out. The placement of this point is by a high-resolution LiDAR sensor, but that is both expensive and hard to implement for our use. The proposed method from the study is velocity potential APF. Essentially, it converts the attraction and repulsion forces into Cartesian velocities using a scaling factor. These velocities are transformed into joint velocities using the inverse Jacobian matrix, and you can see a picture of how that might look like there in the first image. The overall algorithm follows the chart in the second picture, where you can see it finding the smallest distance between 2 points, applying APF, finding the forces, and associated velocities. Next slide. The authors tested a 6-degree of freedom robot arm in a static collision avoidance simulation in MATLAB. From the first figure, you can see how a collision between the two arms might look like, and the second figure shows all the motions of all the motions of both arms, trying to avoid collision using a rigid body tree model. Lastly, from the comparison graph and the table, we see the relatively fast conversion speed and simulation efficiency of the velocity potential APF. Do note, however, that the method has a somewhat longer simulation time due to the constant calculation of distance and the inverse solutions of the two manipulators. And the authors suggest a parameter optimization as an avenue of further research, which is where our testing comes in.
So for our implementation section, we compare the traditional APF algorithm to the velocity profile algorithm on a 4-degree of freedom quantum arm robot, which is seen here on the left, instead of the dual arm 6-degree of freedom robot that is presented in the paper. We considered 3 different static environments and 1 dynamic environment to simulate the algorithms on. Our goal is to determine the effect of the different scalable parameters, these scalable factors, and how they affect the performance of the robot. So the first scalable factor we consider is K attraction, which scales the attractive force that pulls the end effector towards the goal. Then you have the K repulsive factor, which scales the repulsive force from the obstacles. And then you have the rho theta, which defines the effective area of repulsion around obstacles. And then the environments we simulate on are shown here. So the first one is just a simple environment with 1 obstacle present, and it is not in the way of the end effector and the goal. The second environment has 3 obstacles present, with 1 of the obstacles present in the way of the end effector and the goal. and the third environment has two obstacles present in the path of the end effector and the goal. We also simulate on a simple dynamic environment where the obstacles translate in one direction as a function of time. So before we start discussing our results, it is important to identify what we based our performance on. For this, we copied some parameters from the paper, and we also added a couple of our own. So performance in our simulation is based on the time that it takes to reach the end goal, the average speed of the end effector, the path length, and lastly, the number of iterations to reach the end goal. So based on multiple simulations with the two algorithms, we conclude the following. We conclude that the K attraction and K repulsive scalable parameters do not have much of an impact on the performance as long as the difference between them is significant. We note that the road data has a major effect on the performance and should be refined depending on the specific environment the robot is in. We also note that the updated APF algorithm and the traditional APF algorithm perform similarly in simple environments, like when there's only one single obstacle present. But we see that the updated APF performs better than the traditional APF as the environments get more complex or multiple obstacles are introduced. This is also the case when we simulate both algorithms in a dynamic environment. The VP APF algorithm performs better. One downside of the updated APF algorithm is that it requires more computational power as the number of iterations increases as the environment gets more complex. So one thing that we would like to do if we had more time or a third person in our group, we would consider more complex dynamic environments instead of just a simple one where the obstacles translate in one direction. Or we would even consider applying the updated APF algorithm to a real life robot manipulator in the robotics lab. I would like to show one simulation with the dynamic environment. This is the velocity profile APF algorithm simulated in a dynamic environment. So as we can see, the obstacles are kind of translating in the X direction. And the robot manipulator is accordingly, I guess, avoiding the moving obstacle. So by changing the row data constant, we can determine how close or how far the robot arm gets to the different obstacles. In certain cases, when the row constant is too high, the end effector is unable to determine a path to the end goal. I think that's about it. Yeah, okay, so it's reached the goal. Thank you.
Thank you.